All right, welcome everybody. This is the fourth installment of the winter webinar series, Updates from Michigan's Western Lake Erie Basin. This webinar series is designed to provide our community with updates about ongoing projects to monitor and manage nutrient pollution in Michigan's portion of the Western Lake Erie Basin. For those of you who don't know me, my name is Allison Bressler, and I'm the program manager of the Western Lake Erie Basin Advisory Group, and I work out of the Water Center at the University of Michigan. So this community group that I work with works collaboratively with Michigan's quality of life agencies and many community partners in the watershed to inform how the state implements projects aimed at managing and monitoring phosphorus to improve water quality in Lake Erie. So the advisory group and this webinar series are generously funded by the Erb Family Foundation, so we want to thank them for their continued support of this work. And for today's webinar, we welcome Tom Zimnicki, the Agriculture and Source Water Policy Director at the Alliance for the Great Lakes, where he leads policy development and implementation across the region. And we're also welcoming Ed Verhamme, a principal and senior engineer at LimnoTech in their Ann Arbor office. He's also the president of Freeboard Technology, a subsidiary of LimnoTech that focuses on building, deploying, and maintaining new monitoring technology. And they're going to talk about the new concentrated water quality monitoring efforts that are happening in the Western Lake Erie Basin. So a few housekeeping things. As you think of questions, please feel free to just put them in the chat as you think of them. There will be a question and answer session after the presentation. During that Q&A, you're welcome to continue putting questions in the chat, or you can raise your virtual Zoom hand and I will call on you to ask a question. I will note if you have general comments or links you want to share, just post those in the chat. All right, so now I'm going to pass it off to Tom and allow screen sharing. We can get started.
Thanks, Allison. And thanks for pulling those slides up, Ed. Hey, everybody. Good to see everyone. Appreciate the invitation today and excited to walk through this project. So we've structured this. We're gonna have like 25 minutes or so, maybe 30 minutes from us, and then we wanted to leave quite a bit of time for Q&A from folks. So I'm excited to get some feedback. So Ed, if you want to move to the next slide. And you can just kind of, leaf through. So a couple years ago, stop right there. That's good. A couple years ago, the Alliance as well as LimnoTech kind of worked on a project that really wanted to better understand both the cost and the scale that would be required to meet that 40% reduction target in the Western Basin. And so we partnered with the Ohio Environmental Council and the Delta Institute to run a series of BMP scenarios across the basin, and then figuring out the associated costs with that as a way to kind of put things into perspective about, how close or how far off we are from both the scale and the funding necessary if we were simply trying to buy our way out of this problem. So Ed, you can go to the next couple. So after that, we published that report. Happy to share that around. We've presented on it a couple times over the last 2 years or so. But from that, we had a lot of conversations with the Department of Ag in Michigan, who really wanted to see if we could run a similar analysis at a smaller Huck 12 scale. That's really the scale that the state is working on from a conservation planning and implementation standpoint. So it only makes sense, right, to understand scale and cost at the geographic scale that the state is actually working in. So we finished that similar report last year. Again, happy to share that around. Ed, you can go to the next one. And then some of a high level takeaway from that, we developed a couple decision support tools to kind of better understand where priority fields would be from a targeting standpoint. And so this kind of gradient table in the middle, there were a couple similar tables like that in the report. And then we used the methodology to then create these maps that you see for each of the sub-watersheds, that really gives kind of a heat map of, if conservation districts or the state was going to go out and find, highest priority fields, this gives them a place to start, as opposed to just kind of cold calling folks. So you go to the next one, Ed. So we all know that models are imperfect, right? And they are an important tool, but they are just kind of one tool and one piece of information when it comes to understanding, how and where to put in conservation. And so we put a proposal, we being the Alliance and LimnoTech and MSU, put in a proposal to the Erb Family Foundation to really understand water quality at this smaller Huck 12 scale. We floated that to the state as a project that we were going to do, and the state expanded that effort, right? And so we last year launched this water quality monitoring project across the the priority sub watersheds that MDARD and Eagle have identified. I'm not going to read through all these bullets, but you can see some of the high level kind of summary points of what we were trying to better understand with this monitoring. The project is really built around high density at a finer spatial scale than what we've done in the past from a monitoring standpoint. So Ed, if you want to jump to the next one. So here is a map of all of the monitoring locations that we have. The red and yellow dots are the new locations that are going in or that are already in as part of this project. We have 50, give or take, new locations across these 5 sub-watersheds. And then the gold and brown, boy, Allison, you weren't kidding. That dinging is distracting. The gold and the brown squares are current USGS, both flow and water quality locations as well. So a number of these locations are complementary or paired with existing USGS stations. Ed's going to walk through all of the equipment pieces of that, and we'll talk a little bit more about some more of the details about where some of these sites were located. You can go to the next slide, Ed. Also, as part of this project, we're also doing some tile drain monitoring, some new tile drain monitoring. Originally, we were gonna put a tile monitor, just one in each of the sub watersheds. We decided that it would probably be more useful from a data standpoint to concentrate all of the tile monitoring in one of the sub watersheds. And so we're putting those in the South Branch near Adrian. And so we'll have 5 tile monitoring stations. MSU IWR is largely leading that aspect of the project. IWR is also leading in the SWOT model updates and some other model updates using both the data that we're collecting here, as well as newer weather data, which hasn't been updated in a number of years. You can go to the next slide, Ed. So we have kind of 2 parts of the monitoring here. And again, Ed is happy to get into a lot of detail here, but we have kind of this online sensor component of the monitoring. The one that I want to draw folks' attention to is the real-time orthophosphate monitoring that we're doing. We have those in 10 locations across the 5 sub-watersheds. And so those are pulling samples on a much continuous basis. We're also doing what I say to people, and I'm sure scientists in the room would balk at this, but kind of the more traditional water quality monitoring, focusing more on ISCOs and grab sampling. And so we're doing that in conjunction with kind of this really expansive online sensor network across these 5 subs. The project and the monitoring runs through 2029. All the data is going to be available, both kind of in its raw form, as well as some summary data, which I'll get into in a second. So Ed, if you want to go to the next one. So part of the data analysis and part of what is going to be available to the public is kind of this summary format, that this is just a mock on the right-hand side from MSU, but something that really allows both the public as well as just any interested party to kind of get a quick Reader's Digest version of what's going on in the watershed. And so the data that we're collecting from this project is going to be plugged into the IWR site as well, along with some other data that MSU is aggregating. We've hosted a couple of field demo days in the fall of 24, both in Adrian and Saline. We had really good participation from a really wide range of interested parties, from state and federal agencies to NGOs, as well as some folks from the legislature. We have another field day demo coming up in June, which is in partnership with the U of M Water Center for their the WLEB advisory meeting, as well as that conference. We've reached out to the conservation districts to have district meetings, which are likely going to happen in the fall of 25, again, as a way to just kind of share what the project's all about, as well as kind of solicit feedback from folks on the ground. If anybody has ideas of other groups of folks to talk to, please send us an email, drop something in the chat. We're happy to do these demos as much as necessary. And then if folks want to stay up to date on the project, we have the Alliance set up a landing page on our site. The link is there. And so there you can find the quality management plan for all of the instrumentation and the data collection, summary videos, and just summaries of the project. And so if you need to share kind of information about this in a condensed, quick way, you could send folks that link. So I'm going to turn it over to Ed, who's going to run through some of the equipment and then some preliminary data that we pulled at the end of 24 and the beginning of 25.
Great, thanks, Tom, and hello, everyone. I just wanted to remind you again to drop questions into the chat. It'll help when we transition to that part to have some questions in there. And there's no bad questions. I always enjoy hearing what people think is interesting and why we're doing parts of this project. I wanted to re-present the station map and just impress on you the scale here. Ann Arbor is just on the north side of the map. Toledo is just off the south side. And these are the 5 priority sub-watersheds. Each one has a unique characteristic, and part of this project was understanding how to monitor at this smaller scale, and how do we even site locations, where to site a denser network, why is that different in this watershed than the other? And you start to see some watersheds have lakes, some have heavy ag ditches, flat. So it's been a whole part of this project is just getting into these headland watersheds, which are heavily ditched and managed for water flow. I put the land area here that each watershed encloses, between 24 to 71 square miles. Looks like I forgot this, that's the point, but that's about 24 square miles as well. The other part of this is actually getting these stations sited and installed. We're on the public right of way, so all of our stations are really at the intersection of the county road right of way and the drain commission right of way. So it's kind of, you think of a cross of each one of those organizations owns the road there and manages the right of way for the ditch. So our sensors they're pretty small and pretty discreet. But just getting that permission. So we had to apply for 135 permits as part of this project, every location with 2 organizations, and then sort of some master ones with Eagle and the Army Corps as well. So that was a big logistical challenge to get started, all the documentation, the site information, site visits. And I did want to acknowledge all those partners that worked with us on this. If we zoom into one of the sub-watersheds, this is the Saline River watershed, shows the land use data as a backdrop and some of the hydraulic network. There's a USGS station that was just installed here at this Austin Road location. And our approach for the project was to install, I believe we have 11 stations here. There's the purple circles and then the yellow circles. All locations we're monitoring level, turbidity, temperature, and conductivity. And then at the yellow ones, we're adding an ISCO and an online SRP analyzer, as well as weather, rainfall, and soil. So there's really, as Tom mentioned, the two types of monitoring are the sensors, and then we're also doing grab sampling at all of these locations, and with some specific focus of ISCO sampling. So we cited the locations to be kind of distributed throughout these sub-watersheds, getting some in a couple square miles of land area upstream, some right before another smaller tributary joins it, some upstream and downstreaming of lakes to understand the impact of that storage. So just a really good coverage of these small sub-watersheds with a varied small and medium-sized stations. If we look at that station type 1, where we're doing turbidity and level stations, this is what it's going to look like. Pretty discrete radar level sensor that's got a accuracy of 1 to 2 millimeters. We also installed a optical turbidity sensor and a temperature conductivity sensor that go in the water. We use various PVC pipes and posts to try and protect the tube and keep those online sensors in the right location. It's been challenging to think about how much water level changes throughout the year between going completely dry to having 3 to 4 feet of water on every inch or 2 of rain. So a very dynamic, small streams, and siting traditional water quality sensors just take some planning and thought. And then these are our small boxes that have the battery, cell modem, and solar panels on board. So just kind of a turnkey way to get this sensor data online. Station type 2 includes all of the sensors from type 1, plus an ISCO box here. This is a refrigerated ISCO station where we have a solar powered batteries on board, and we can cool those samples for a few days with some battery power. It also has I call it a sidecar of our online nutrient analyzer. So we're able to pump water from the stream, store a sample for some whole water analysis, and also process an online nutrient sample to get that SRP result. That SRP sample is being collected every 2 hours. So we get a really nice continuous measurement of that, along with turbidity and temperature and conductivity. There's a weather station at this site as well, and you can't quite see the right angle, but there's a soil moisture and rainfall gauge here. So these are what we call our master stations. If we look at the sensors and what we're using. We have rain gauges, optical turbidity and temperature conductivity sensors, weather stations, radar levels sensors. The boxes that contain the refrigerators, online nutrient analyzers, it took a lot of thought thinking about the footprint, the size. Traditionally, this would be like a small building with 110 power, trying to keep costs down and trying to think about how we do this at 10 sites. This is the type of enclosure system we came up with. It took a lot of thought to batteries, charging, electronics. Every one of these stations is remotely accessible. We can program that online analyzer to sample more frequently or less frequently, and we can also remotely trigger the ISCO to collect water samples and help time when it's going to fill bottles. There's a whole army of people behind not only building this specialized equipment, working with all the reagents that are going to be required to be kept inside the enclosure to keep the nutrient analyzer running. So that's, again, a big part of this project with 50 sites was sort of thinking about the size, the installation method, as well as minimizing the time from permits to actually getting the equipment running. Again, just a little look at the people power behind building this here out of our Ann Arbor office, and then deploying it really over a two-week period. We had the majority of the equipment installed, and some siting and testing later into fall of this past year. You can see what some of the sites start to look like. Lots of ditches, culverts, small bridges that we're working with. The other part about working in the public right away is we're just parked on the road, maintain the sensors. We don't have to hike in and worry about too much access for taking samples. This is, again, a look at just how we install those more sophisticated sampling equipment. As I mentioned, all this sensor data gets posted online. So an asset of this project is being able to watch these sub-watersheds, I'd say, come alive when it rains. We can see the rainfall, we can see the soil moisture go up, we can start to see water level change. Because we chose radar sensors at 50 locations, they're ultra accurate. We can see when farmers actually irrigate, because we can see the few millimeter rise in that water level of runoff happening. We can see even evaporation happen and few millimeter drop. We can see just really interesting hydrology signals, and I think that's where we're starting to look for the difference between impacts that humans are causing versus what's a typical rain event look like in the spring and the fall. We can also use this online data and dashboard to help our field crews respond for wet weather events. So to know when we're going to hit the peak of hydrographs. This is showing just the rainfall data, soil moisture data, and what that water level data looks like. It was an extremely dry past 6 months. This one station here, LC1 Lime Creek, we only had 3 events that had the water level rise since September. One was just this past week with this 50-degree weather we had yesterday. So this is through yesterday. Just to highlight some of the real-time data, we because it was so dry last year, we only did I just call it it wasn't a dry weather event, but it wasn't wet in September. We went through and collected water samples. We have some idea of what the total phosphorus and SRP is, but we're really waiting for this spring after we install all the sensors, and we're going to get some, we call real rain events rather than what we had this past fall. But just looking at this SBR9 site where I showed a few pictures of the installation, we had 1.5 inches of rain in October. And I just wanted to step through some of the sensor data. Oops, sorry. I just wanted to step through some of the sensor data. So in October, we can see that we get 1.58 inches. We got a 10-minute summary of that rainfall. We can kind of see how fast it hits the landscape. We saw even 12 hours later, we had a little tenths or hundredths of inches of rain, which it seems insignificant. We can certainly start to see those little tiny events on events in our data streams. This is the water level data from that site. And even though we had the very tiniest amount of additional rain, you can see that bumped up the water level a few, this is millimeters. This is 5 millimeters, the water level rose after that rain. Our goal is to get stage discharge relationships at every one of these 50 sites so we can actually translate water level to flow. One nice thing about this dense network is flow is going to be relatively conservative, so we can have a easier time of generating stage discharge because some sites are downstream of other sites where we'll have flow estimates as well. So it's nice to have this density, look for patterns, and understand how that landscape is operating at this small scale. Conductivity measurements at that same site. So we saw water level rise. We see conductivity drop, which shows we're getting some dilution from rainfall, which is nice to see. We're also seeing a rise in turbidity coming a little bit after the peak in level. And our online nutrient analyzer at this same site is also showing a rise from about 50 micrograms per liter to a little over 150 micrograms per liter of SRP. So at this point, we've got all the sites identified, all the equipment installed. It's been running. We've had a good 6 months of all the water levels and sensors installed. We did remove the turbidity sensors for the winter. They have a mechanical wiper that moves around that we don't want to break. So our plan is to reinstall the turbidity sensors and sort of be ready for a growing season monitoring program this year. I did want to do a time check. I got a few more trends I can show. It looks like it's
You have time.
12:30. All right, I'll go maybe 5 more minutes just showing a few more data trends. It's, the online dashboard, you can just sit there and every event, you can just watch these events come through. And it's fun to see, as a scientist, just the signals you're looking for in expectations of how much turbidity is going to rise. I wanted to highlight this Lime Creek watershed. So again, this watershed at the mouth is about 42 square miles. We've got 11 stations here in this sub-watershed. The main branch kind of snakes its way up towards Line Lake. We have a location upstream of Line Lake, which there's like no storage in this system upstream. Then we have the lake, and we have a few stations downstream. As a modeler, I can start to see what is the mechanistic model trying to understand with how water moves through this system. But we never really had data at this scale to check the basic fundamentals of, is that storage at Lime Lake right? Are we going to match what the impact of this Durfee Lake and its outlet is? And so I think the time scale and the spatial scale of this project is pretty unique, and especially thinking what landscape models can even be applied at this scale, and how do we use this type of data. Looking at the weather data again for this sub-watershed for an event, we got 1.87 inches on the 29th. This was right around New Year's. And then we got a little bit of rain right after. Soil moisture again. Soil moisture again shows, yep, the ground got wet, dried out a little bit. We got more rain. We see that soil moisture rise. Soil temperature is also in here, so we can see if we have frozen ground or not. Looking at the water level data from upstream of Lime Lake, I said there's no real storage in that system. We see water level rise in just a few hours. It rises. It's about about 36 hours, and this event is over. from a sampling standpoint, it's going to be extremely hard to be right out there at the peak of this event. So we're going to have a grab sample program. That seemed like we would have been able to catch a grab sample at some point in this. It'll be nice to have the turbidity data to see how does that respond, what was our SRP measurement, how do we understand the volume of water moving past this site. Moving downstream of Lime Lake, we can see the lake is acting as storage. The lake is filling up, draining slow, as we'd expect. Moving to a slightly different site downstream, again, we can see a very fast rise in that, and the shape of this is again characteristic of the landscape, the soil, the runoff, where the field's covered, things like that. So we did a grab sample event, as I mentioned, on November 6th. This shows the TSS data that we saw during that. We actually had some dry sites. I mean, there was no water present. We're so far upstream that we'll have to be ready and watch the size of the events. The soil here was also extremely dry, so it was an unusual drought for this event. We had TP concentrations, 0.1, 0.4, DRP. This is a filtered sample analyzed at the lab. We're also measuring things with the YSI instrument. One thing that's notable is we were seeing low dissolved oxygen at some of these sites as well, and turbidity into the hundreds. So all great data, knowing we're collecting lots of data, and we're going to have a huge data set